Continuing the teardown on the NiteIze Bike Light for manufacturing cost reductions, I just wanted to quickly review where we're at and where I'm going next. So, high level, I've owned this bike light for a number of years, and I started looking at it from a manufacturing standpoint, realized that it feels like there's more parts in here than need to be. And so I built an engineering bill of materials. I started an engineering 3D model, and I would just like to talk through kind of my thoughts about this device. So inside the package, we have this device, and I've kind of gutted it in order to take some dimensions off of it. But here's some of the details that might be interesting to think about. So inside the bottom was this chassis assembly, and we'll cover that in a second. The bottom itself is a two-piece overmolded, let's say ABS lower cover. Now, interestingly, from the top view, you can see that there are side actions required in order to pull these four features. So a side action is a moving portion of the tool that must get out of the way for this part to eject out of the mold. So these parts right here are, in fact, trapped in the tool. The steel required to create these features is trapped in the tool unless those parts are pulled out of the side. So side action or a slide that must be opened up in order for this part to be ejected. If we ignore those four features for a moment, those aren't a super complicated slide or a side action, but it does increase cycle time in the mold, which increases part cost. Also, it reduces the amount of cavitation or the number of cavities in the mold that we're able to get in a tool simply because we have slides or moving parts in the tool. So the more we can keep our parts sort of a standard open-close design, the better. We can increase the number of cavities, which reduces or increases the number of parts per mold cycle, which reduces our overall cost. So ignoring these four tabs, the rest of the part is generally an A-B part, meaning it pulls A and B. All these ribs are all straight vertical, and from the bottom side, most of this is straight vertical. However, there's one other feature here, and that is this little notch in the side. So another design decision that was made, presumably to help open the device up, so when this is locked in place, maybe it's a little bit difficult to open the device, so they made this little notch here, thinking maybe you could stick a coin and pop the lower cover off. That's kind of the thought. However, from a molding perspective, there's no reason that this upper edge of this feature needs to be here. So this could have been an open, an in-plane mold direction feature. We could have had this lower lip, which would allow you to pry it out of the tool, but you wouldn't need this upper edge on here, which would eliminate this side action. Now, as discussed, we already have a side action on one side of the tool. So essentially this feature would be free if all three of these came out with one side action. But it's not totally obvious to me if that's the case, because I don't see any mold actions other than possibly a parting line around here, where maybe this was a single side action. Nonetheless, even if we could get rid of one of the side actions, we could increase cavitation, so we generally could simplify this part a little bit by removing some of these tabs. But this isn't the most offensive part. So we'll continue on. Oh, by the way, the bottom surface of here is a TPE or TPU overmold part. So inside of the part, we have a rubber face, and that's so that as you bolt it onto your bike frame and we strap it on, this prevents it from vibrating and sliding around. You'll notice that there is a rigid rim of plastic all the way around the outside of the part, and that's what we call a shut-off surface. The shut-off surface is where the mold would close up tightly. The TPE would be injected at this gate mark right here, and it fills up to that clamped surface. So that TPE needs somewhere to flow over the edge, or sorry, up to the edges of that part and have a clean shut-off surface. So many times on overmolds for grips for say tools or electronics, you'll see that there's a small little edge right here, and then generally that's not avoidable from a molding standpoint because the edge needs to have a clean shut-off surface. If these two faces were parallel, meaning if they were coincident with each other, what ends up happening is the TPU or the rubber would flash out between those two faces and cause an aesthetic imperfection. There are a few other things to note. There's some logos and decals on the bottom here that are in the plane of the mold. So those are essentially free, some mold markings here, and the gate from this part. So overall, a decent little part. We'll move on. The chassis assembly, which drops inside of this enclosure, is 3 separate components. So we have a circuit board assembly, and in this case, it's actually 2 circuit board assemblies. We have the LED circuit board and the button board, as I'm calling it. The LED board is pretty straightforward. A couple of components on the bottom and a solder joint where we hold these together. Now, the solder joint's actually a relatively low-cost method of connecting 2 boards together. We don't have a connector to place, and for reliability, this is actually a really clean joint. So this is a low-cost assembly right here. I don't have a problem with this as designed. Surface mount LEDs are going to be a little bit maybe more expensive than these through-hole mount LEDs are going to be a little bit maybe more expensive than a surface mount component. Surface mounts can be placed in a line. Some of the LED components are generally going to be manually placed and then soldered, although there are some automatic through-hole component placing. But if we could do surface mount LEDs here, potentially those could be a little lower cost on the PCB. The PCB is wired to the battery terminals, so when we get to the bill of materials, I'll explain how this all works, but we have a molded chassis component with 3 separate battery contacts. We have a dual contact, which is a spring and a pin, and then a spring and a pin, so 2 of those. Then we have a spring contact and a pin contact. Each of these is wired up with a small, about a 30 gauge wire, and those wires are through-hole soldered directly onto the PCB here. So through-hole soldering, again, low cost, no components, no connectors to assemble. So that's a reasonably affordable feature. I don't think I have any problem with that. This chassis part, though, is kind of interesting. We have this rim around the outside, which is a plastic molded part, which means we have a mold that's created, built, validated, and tested to make this ring. And this ring, from all I can tell, does basically nothing. The only thing it does is it aligns this board with the top of this chassis. But that means they're making the part, they're adding 4 screws, which is all labor, and assembling it, and then putting this board on here. Now, if we were to just take these 4 screws out and eliminate this part, the whole thing would work fine. We could have a couple of alignment pinholes on this board with a couple of alignment pins coming off of the lower chassis part, and this PCB would connect directly onto the chassis. We don't need to support the edges of this board because there's no loads going into it. And if there were loads going into it, we could have ribs coming off of this lower part that come up and support the edges of the board. So these are some of the changes I'm going to model into my assembly and do a A to B comparison. But simple changes like that, eliminate an entire component, eliminate 4 screws, completely simplify the way that this all comes together. The rest of the chassis component, though, is pretty clean. I think it's a pretty well designed part. There is an undercut in this part and in this part required for the battery terminal contact, which could have been avoided if this part were allowed to be sitting on the face of the part rather than sort of flush with the part. And since this is a non-aesthetic part, meaning nobody's ever going to see it, there's not any real reason why these had to be flush, but making them flush on the inside means that we had to have a sort of a lifter or a manual hand load insert or something on the inside to create that recess so that this part wouldn't become trapped in the tool. So overall, I think there's a lot of opportunities on this little part that could be improved as we go to what I'm calling my Gen 2 design. Lastly, there's two little tabs that stick out here, and I'll cover what those are for later. But those tabs are essentially free. They're in the direction of pull. There's no undercut on them whatsoever. So the mold can create these two tabs essentially for free. A little bit of iconography on the bottom showing how the battery icon or battery installation works. Again, that's a free feature. I like that as well. This little ribbon is held in place with a little heat stake right here, what appears to be a heat stake. So I'm going to pop this open, see what happens here. This is actually another part that I need to add to my bill of materials. So this is a little plastic molded piece that presses over a few. So that's a little plastic dog bone piece that presses over a couple of pins on here. I think that could also be cost optimized, because this little strap literally does nothing. The only reason this strap is here is to help reject the batteries. So very low loading on this thing. I would not design and install a custom piece to retain the end of this thing. This strap could have been a dot of hot glue and press this thing in here, and that would be fine. Worst case, we could have had a hole through the end of the strap, press it over a little pin, and heat stake it onto the end of the enclosure. I would not add these additional parts. Parts equals cost, logistics, tracking, inventory management, labor, quality assurance. Lots of issues why we should not add an additional part if we don't need it. So yet another reason why this chassis needs to be rethought. Lastly, there's a little side action here required just to create a slit for this strap to go through. And I think there's probably a cleaner way to do that, because this mold opens and closes like this, and I could create a sliding shutoff between these two faces that doesn't require a direct side action in the tool for this little slit. So I'll do something like that when I redesign this part as well. The lens part itself is it's a nicely designed part. I actually really like the lens. It's mostly an A-B part from what I can tell. So I split this into a couple of pieces here, but the part sits in a lip groove around this upper edge. And that lip groove comes up and around the top here. But the lens is a A-B part. It's really clean, simple, no undercuts, no additional ribs, no features. I like the lens part a lot as is. This upper piece here is an interesting one. So I'm calling this the upper enclosure, and the upper enclosure is really an assembly, but because it includes this button is kind of a TPE, a rubber part here that allows us to reach in and press on this tactile switch on the button PCB. So that right now, my initial thoughts were that this was an overmold. Overmolding is fine. However, there's something about this that makes me think it's not an overmold. First, I don't see any mold parting lines around this joint that would lead me to believe that we could have gotten a tool in here and pressed against that housing tightly enough to get a good clean shut-off face on there. Now, it could have been a two-shot mold, meaning that the mold opened up, or the first shot was the ABS plastic, and then a mold cavity opened itself and then injected the TPE. But I just don't see that happening. Not on this part anyway. I could be wrong, but I don't think so. And here's another clue. If I turn this thing around, we'll see on the inside. We can see on the inside that there is a step from the inner housing to the inside of the button part. And then there's a small raised bump in the middle of the button. Now, what that tells me is this tool would have needed to reach in and press into the opening that was left when this button was created. And if I'm going to try to push this out, actually, because I'm in destruction mode, let's see if I can push this button out and see what happens. So when I press on it, see that edge is starting to separate from the housing here. And we'll see how well that is. bonded in place, or if I think it might be injection molded. I could be wrong here, so we'll see. This is, okay, so this is interesting. We have holes through the housing. Holes through the housing right here imply mechanical bonding. So I stand corrected here. This is an overmolded button. And the reason that the reason that this tells me this is a lot of times when designers design a rubber button, what they're looking to do is create a strong chemical bond between the two surfaces, molecular bond, where the TPU and the substrate, or the ABS, are molecularly bonded, meaning that they attach to each other and they will not release. This is a perfect situation when that happens, and a lot of times it doesn't happen. So say you put a silicone on top of a polycarbonate or something, you can get a good bond with some materials, but a lot of materials tend to reject each other, or they just don't bond perfectly. Temperature matters, surface energy matters, preparation matters, priming of the surface is sometimes required. All these things are necessary, but in this case, when I open this up, what I see are mechanical locking pins. So what this means to me is that this was intended to flow the rubber material through those pins and create mechanical locking features through the wall of the part. So this is super cool, actually. I'm impressed. I didn't see this at first because I didn't see any mold parting lines on the outside, and I thought that this undercut on the inside was a little unexpected, but this is cool. So when I pull this off, now I can see that those features, these little rubber pins, are not assembled into the housing, but those are overmolded onto the housing. So now we can be assured of that. It's really interesting now then that they did have a tool that reached in and created a recess inside of here. If I redesign this button now, I'm going to try to simplify that tool, because if we can simplify the tool and remove that side action necessary on the inside, we can then also reduce the mold cycle time, which reduces part costs and everything else. But overall, super cool. So that's a nice little part. That is the sealing surface on the enclosure, and that presses up against there. So cool, learned something about that. These holes and this entire face right here, including up to this chamfer right here, is really a big undercut and must be pulled out of the tool this way. So when this part is molded, there's a big undercut on this face. There's also an undercut on each of these hooks. Each of these hooks is retaining one of the O-rings. So when I snap this into here, the O-ring doesn't come off. So undercut on this face, 2 undercuts on this face, and then we turn the part over and we have 2 undercuts on this face. These are due to the locking tabs from this lower part. 2 undercuts here, 2 undercuts here, and remembering these hooks on the end of the chassis, we have an undercut on each end as well. So this thing has 6 undercuts on the inside. 6 slides lifters are required to open this part up on the inside, plus 1 on the outside face, plus 2 on this face. And if you look around closely, you can start to see these witness marks on the sides of the part right here are those lifter or slide marks that indicate how they pulled the tool out from inside of these hooks, pulled it out this direction, and then the tool was allowed to open. And it looks like otherwise the rest of the part has pretty good draft on it, has a little bit of surface texture, maybe a MT11010 or so, kind of a light bead blast texture. And given the 5 to 10 degrees of draft that's on this part, that's a pretty appropriate texture. Final note on this part is that once it's assembled, or at some point in the process, they're applying a pad printing stamp on one side and then turning it over and applying a pad printing stamp on the other side. Pad printing is a manual process. It can be automated, but pad printing a color on a part means that we need to fixture it, hold it in place, pick up some ink, and transition it onto the part. And then we turn the part over, pick up some more ink, move over and transition on, stamp it onto the part. And then we have to let it dry. High cycle time on those operations. And if we could have instead molded these design features directly into the housing, these design features could have been a spot polish. They could have been a texture change and eliminate that pad printing feature. So I think there's a number of opportunities here to reduce part count, reduce part complexity and tool complexity, to simplify the molding strategy and reduce your molding cycle time, reduce part count. I didn't mention also, this is overmolded here, but it's also overmolded along the bottom edge right here. So there's a main seal that comes just over the edge here, right here. This is a soft rubber edge, and it appears as though that molded seal is fed through the backside of this part. So it's injected here, the rubber goes through the part and comes up to the upper edge and then fills out this upper seal. So that's kind of a clever way that they saved a little bit of cost. They made one tool to create two rubber seals on, or two rubber features on one substrate part. Kind of a neat thing that I noticed. So overall, I think a number of opportunities here. And next, I'd just like to show you briefly my CAD model that I've started to investigate these ideas. Okay, so I have modeled up the entire device here, and I've broken up the features by kind of starting with the batteries. I'll just kind of roll through the tree here. So starting with the batteries, which is kind of the core base of the system, I built in the chassis, which is holding the batteries. I threw the printed circuit board on top. And again, I'm starting from the inside and working my way out because the outside surface has to depend on everything that's inside. I next built out the main body shape. With some surfacing, and you'll see that once I add in the button and the lens details, I can start to see how this whole thing comes together. Modeled up the main seal, and then worked through the aligner part, the rubber bottom, lower latches, and the pad printing. And in the assembly, you can kind of start to see what this looks like. So here's all the parts. The lens, the upper housing with all of its side actions and shut-offs. The PCBs, the PCB aligner part, the chassis. Again, I've simplified the chassis a little bit. I don't need all the features. What I'm looking for is a representative geometry so that I can get quotes. And then the lower part down here at the bottom with this little coin pickout area. So overall, I have a representative CAD model that will allow me to get some cost quotes, and then to compare those cost quotes to an updated, simplified assembly model. So stick around. That's what's coming up in the next few weeks.